By the way, some people are asking if the test would be online. The test would be in person, okay? So you need to come here on Monday at 11. So we have 3 different rooms for the test. Some people will be here, some will be in other rooms. Okay, so again, this is worksheet 6. So for the free body diagram, the first thing you need to do is define the coordinates. Okay, so this is for the first example. So define coordinate system. We define coordinate system as the right to be positive x and up to be positive y. Okay. Down to be negative y, we don't need to write that, and left to be negative x. So that's the coordinate system we are using. And then represent your object with a dot, okay, a solid dot mark. So that's the object, which is in this case a heavy crate. Okay, so the heavy crate is this dot, and then think about how many forces you have there. So when you hang something in air, it will be attracted by earth, or it would be pulled by earth, which we call the weight, okay, weight of the object. So weight, there is weight due to the gravity, and there is something holding that object. That's why it doesn't fall. So what is holding the object? The steel cable is holding the object. That means the steel cable is providing some kind of force, and that force is called tension. We talked about that last time. So when we use a rope or string or cable, it should be straight. Okay. So that force is called tension. And this object is not accelerating. So it will not accelerate only in the case when this upward force and downward force are equal. Okay. So for example, if you apply some force on an object, this force will accelerate this object. Okay. But if you apply same amount of force on the opposite side, then this force will be cancelled by that force. That means there won't be any acceleration. So in order to have an acceleration, you need to apply unequal forces. Okay, one bigger force and the other smaller force. Then you will have some acceleration. But if you apply same forces, then the acceleration would be 0. So here, we do not have any acceleration. That's what the question tells us. Moving at constant speed means no acceleration. V is constant. That means we need to have the equal forces on up and down. Okay? So that's the free body diagram. So free body diagram has the object and the forces that are being exerted on the object. So in short form, it's also called FBD. And here in this case, our net force, total force, is 0, because net force means sum of the forces. One is T, which is pointing up. The other force is W, which is pointing down. Okay? So when you put the minus sign, you don't need to put the arrow here. And these two are equal, so they'll cancel, so 0. Okay, net force is 0. Let's look at another next problem. a boy pushing a box across the floor at steady increasing speed. So why don't you guys start this one? Okay, so first thing is again draw the coordinate system, visualize the actual picture of the problem, and then usually it's simpler and easier to consider the surface as your x-axis. Okay, if you do that, it will make our job easier. So consider the surface to be x-axis, and perpendicular to that would be y-axis. So that's positive y, that's positive x. Okay. Now let's draw or represent the object by this point or this dot. So that's the box. Okay. And now think about how many forces are acting on the object. So the first force, what's the first force? The first force would be the push of the boy. Okay. So we have this force. Let's call that F sub B. Okay, force exerted by the boy. Another force is, it doesn't say the surface is frictionless or it has friction. So when it doesn't say it's frictionless, we need to consider the friction. Okay? So there is friction, and friction is always in the opposite direction of the motion. If it is moving this way, then the friction would be to the left. So friction is denoted by small f. We have two kinds of frictions. One is kinetic friction and other one is static friction. In this case, the object is moving, so that means we have kinetic friction, F sub k. What other force you guys can think of? Gravity, yes. So there is a gravity force, W. And the object does not move down. That means there must be equal force in the opposite direction. Okay, there is no acceleration in downward direction. The table is, or the surface is preventing the object from moving down. And what that force that prevents the object from falling down, it's the normal force. Okay, equal normal force. And why did I draw this one longer? Because the net force is in the right direction. That's why it's moving at increasing speed. Increasing speed means acceleration is not zero. Okay, there is unequal force, so there is acceleration. Since there is acceleration, it's moving at increasing speed.
So what's the difference between kinetic friction and
Static friction is you have a box on a surface, you push the box, and the box doesn't move. So what is preventing the box from moving is the static friction. And if the box is already moving, you push it, there would be friction force, which will decrease the speed of this box. So if the box is already moving, it's the kinetic friction. If it is not moving, it's static. Okay, so that's for number 2. Now you also need to write the duration of F net. In this case, our F net, which way is the net force? Our net force is to the right. Okay. So now let's think about number 3. A bicycle is speeding up down a hill. And in this case, friction is negligible, but air resistance is not. If the air resistance is not negligible, that means there is a drag force. Air resistance offers drag force. Now the real case scenario would be it's downhill, so it's like that. So match your x-axis with this surface. So in this case, we'll choose our x-axis to be along the surface of the inclined plane. So that's our positive x, and perpendicular to that would be our y-axis. Okay, that's our coordinate system. Now here our object is bicycle, so bicycle is denoted by this dot. Now think about different forces. So the first force is gravity. It's always vertically down. That's W is vertically down. And there is drag force. So the bicycle tends to move down. That means the drag force would be in the opposite direction. So drag force would be in that direction. Call that D, okay, drag force. And this weight will tend to accelerate this object down. So the weight is pulling this object down, but it doesn't fall or collapse through that surface because there is this upward force preventing it from collapsing. So that upward force here is normal force. Whenever an object is on surface, the surface exerts normal force, okay, perpendicular to the surface. So we have this normal force, perpendicular to that surface. Okay, so we have those three forces, and the object is moving along the surface at increasing speed. That means the net force must be in this direction. Okay, so that's the net force. Actually, this sign is sum. Okay, I don't need to even write that. So I meant to write F net is sum of all the forces. Okay, so you can just write F net here. F net means the total force. So that's number 3. Okay, so number 4. Let's think about number 4. So start the coordinates. Again, this is a surface with inclined plane or inclined surface. So our x-axis would be along that. So that's our x-axis, positive x-axis. And then y-axis would be perpendicular to that. You don't need to write this big coordinate, you just need to write a small one. Okay, it's not necessary to write a big one, just write a small one. So that's positive x, that's positive y. And then in this case, our object is car, so that's the car. Now think about how many forces you have. There is always weight, force of gravity, and it's on surface. So whenever an object is on surface, the surface exerts normal force. Okay, there is normal force. So we have this normal force, and it doesn't say that the surface is frictionless. That means we need to consider the friction. So there is friction force, and in this case, the car is moving, so it's kinetic friction, F sub k, and there is also drag force, okay, because of the air. So if you have two forces in the same direction, there are two ways to represent that. One is by writing two arrows like that, okay, F sub and D. You can draw two arrows, or you can also use single arrow like this, and then draw two arrowheads like that. Okay, one for F sub k, and the other one is for D. So you can use either one, this one or that one. So which way is the net force in this case? So whenever the object is slowing down or it comes to rest eventually, the force would be in the opposite direction of the motion. Okay, so that's the net force direction. So let's say you are moving to the right, but you are slowing down. So the friction is applying the force in this direction, and the friction will be greater than the force on this side. There's no force in this side, but there's more friction here, and that friction eventually stops the object. Okay, so the net force is to the left for slowing down case. In other words, the motion and force have same direction when the object is speeding up. The motion and force will have opposite directions, same direction. They will have opposite directions when the object is slowing down. So in this case, it's slowing down, so the net force would be opposite to the motion. In the previous example, it was speeding up, so the net force is in the same direction as the motion. Okay. Let's look at number 5. So please read the question. So number 5 has different scenarios. In the first scenario, as you hold the rock at rest on your palm before moving your hand. So the rock is at rest. You're putting a rock on your palm and then keeping at rest. So what forces are acting on that? So our coordinate system is up is positive, down is negative. When there is no horizontal force, you don't need to even write the horizontal axis. Okay, if you want, you can write that. But in this case, we are dealing with just the just the vertical component. So that's the rock. It's under gravity, so it's pulled down, and your palm is providing the normal force. And it's at rest, so that means the two forces need to be equal. So they will be equal. There's no acceleration. So that means when there is no acceleration, the net force will be 0. Okay, acceleration 0 means force is also 0, because F is equal to ma. Force 0 means acceleration 0, or acceleration 0 means force 0. Okay, so let's look at B. As your hand is moving up, but before the rock leaves your hand. Now you're lifting your hand up. So that's the rock. So we have again weight. Now it's moving up means it's not very clear whether it's moving up at constant speed or at some acceleration. But let's assume that it's accelerating, okay? So we are accelerating the object. It's moving up and it's accelerating, it's speeding up. That means using this notion, the net force must be up, okay? Meaning upward force should be greater than the downward force. So how many forces we have in the upward direction. The first force is force due to the normal surface or the surface, normal force. And your hand is also pushing the object up. That means you are also applying the force. That's the force of the hand. Okay, so there are two forces acting up. And in this case, net force is up. Okay, so let's look at part C. 1/10 of a second after the rock leaves your hand. So that's the rock. And there is gravity force always. Now what other forces we have here besides the gravity force? What other forces you guys can think? There's air, okay? It doesn't say whether or not the air is absent. We consider there's air. So if there's air, what force will be there? Drag force. Which way is the drag force? Opposite to the motion. The object is moving up. That means the drag must be down. Okay, so we have D and W. So the net force is down. It's moving up. It's moving up. So velocity is up, but the drag force is, or the net force is down. What does that imply? Motion is up. Force is down. They are in opposite direction. Sorry, here I need to write opposite here. Yeah, it's decelerating or slowing down. Okay, so motion and net force have opposite directions. I didn't write opposite here, but that is opposite. Okay. So that's C. Let's look at D. So the rock has reached its highest point and is now falling straight down. So at the highest point, it reaches the highest point and it's falling down. So what forces we have? We have weight again, and we have drag, but this time the drag would be up because it's opposite to the motion. You see the difference? Here motion is up, drag is down. Here motion is down, drag is up. Okay, and it's accelerating. It doesn't say whether it's accelerating or not. Let's consider it is accelerating. Okay, acceleration is not zero. That means the force needs to be, the net force needs to be in the downward direction. The force needs to be longer in the downward direction. Otherwise, if it's like this, then it will move up. Or it will just stop in air. That's not the case. Okay, so the last one. Let's look at the last one. So we have two objects here, object A and object B. And we need to write the free body diagram for object A. Free body diagram for A. I will first write the free body diagram for B, and then I will write free body diagram for A. So for B, this is for B. Okay. I have weight down, and the object doesn't fall freely because this rope is holding this object. That means this rope has tension force T that is holding the object. And we'll have same tension. If you have a tension here, we'll have same tension on this string also. So this weight of this object is pulling this string with this tension. So whenever you write the force, you need to write the arrowhead also. Arrowhead tells us it's the vector. Okay, so that's for B. Now for A, the block A is on the surface. Okay, so let's define the coordinate system. That's positive x, that's positive y. On the surface, it has two forces. One is down, and the same force or equal force on upward direction, which is normal force. It's not moving up or down, not accelerating up or down, so they should be equal. Now this tension is pulling the block to the right. Okay, so there is this tension, and there is also friction. Okay, the friction is exerted by the surface in the opposite direction to the motion. So that's the kinetic friction because the block is already sliding on the surface. And since the block is moving to the right, so the net force, the total force must be to the right. Okay, that's the worksheet.
Can we go over part B again?
Part D.
B on question 5.
This one?
Yeah.
So in this case, it says before leaving the hand. That means it's still on your hand. That means there is normal force. Okay, so you have normal force, and your hand is also pushing it up. That's why it's moving up. So there is force due to hand, and there is force of the weight that is pulling the object down. And that's all we have. We don't have other forces. And we consider that the object is accelerating up. There's net force in the upward direction. Okay. So now let's look at the worksheet 7. So we just learned how to represent the scenarios using free body diagram. Now, how to solve solve force problems.
Do you have any spare worksheet 7?
Yeah, I have. I didn't give you the worksheet. Okay, sorry, I forgot. So please read question 1. So your kneecap, which is patella, is attached by a tendon to your quadriceps muscle, which is shown in the figure. This tendon pulls at 10 degrees angle relative to the femur, the bone on your upper leg. The patella is also attached to your lower leg, which is called tibia, by a tendon that pulls parallel to the leg. To balance these forces, the lower end of your femur pushes outward on the patella. Bending your knee increases the tension in the tendons, and both have a tension of 60 Newton when the knee is bent to make a 70-degree angle between the upper and lower leg. What force does the femur exert on kneecap in this position? So the first thing we need to do is represent the scenario by free body diagram. So let's represent the coordinate system first. Okay, that's our coordinate system. Let's call that x coordinate, that's y coordinate. So the quadricep muscle exerts force or tension in this direction at 10 degrees to the this surface to the horizontal line. Okay, I need to write straight line here. I have hard time writing straight line here. So draw a straight line. Okay, it's not straight. Okay, so that's the force due to the quadricep muscle, or tension produced by the quadricep muscle. Let's call that TQ. It is at 10 degrees. I didn't draw a straight line here because I cannot draw straight. So please draw a straight line. And this tibia bone exerts the force at 70 degrees to this horizontal line. Okay, so this is the tension or the force produced by the tibia bone, and when you apply those two forces, there would be a push force on femur in this direction. So femur, push force on femur. You just call that F or FP or something. And we don't know this angle. Okay, so this angle is 70 degrees. So we want to find this force. Okay, so we want to find F, and we also need to find at what angle does this femur push the bone with respect to the horizontal line. So this is the simplified version of this scenario. How do we solve this problem? We have already seen this kind of problem in lab a couple of weeks ago. So this is in static equilibrium state. Okay, the system is not moving to the left or right or up or down. It's in equilibrium. Okay, so this is in static. It's called static state, meaning there is no acceleration in upward direction or downward direction. Or you can say if the acceleration is 0, the net force in x direction is 0. Okay, and net force in y direction is also 0. Does that make sense? If you have an object resting on table, then there is no acceleration up or down. There is no acceleration right or left. Acceleration is 0. Same thing with this case also. Okay, the whole system is at rest, so there is no net force. There is no acceleration. When the object is at rest, we call it static equilibrium or static state. So when we deal with the vectors, we cannot add this vector with this vector and call that the total vector. The way to add the vectors is split the vector into x and y components and then add x to x and y to y. Okay, that's the way. So the best way is split all the forces into x and y components. Maybe you can make a table like this. Okay, x forces, call that x forces, and then call this y forces. So start with one of the forces. So let's call this TQ, the first force. And what's the x component of this force? We have this vector. Okay, that's the angle. What's the x component of this force? We talked about this last time. So it has x component and y component, sorry. This has x component and y component. X component is this and y component is either this one or this one. So what is this? Is this f cosine theta or sine theta? Cosine. So the side that is touching the angle is cosine, and the side that is away from this angle is sine. That's the way to memorize. Okay. So the x component of this one is f cosine theta. In this case, theta is 10 degrees. And also think about whether this force is pointing to the left or pointing to the right. This component, is this pointing to the left or to the right? To the left. So if it is pointing to the left, you need to put minus sign there, because you also need to consider the direction. Okay, so that's the x component. Y component of that force is TQ sine 10 degrees, and it's up because it's pointing along positive y direction. So that's about TQ. Now let's see TT, the x component of this one. Okay, you have this force. X component of that one is this one. Okay, and y component would be this one. So here is the angle. This side is touching the angle, so this would be TT cosine 70 degrees. So x component is TT cosine 70 degrees, and it is pointing to the left, so we have minus sign. Y component, it's away from, this is the y component, or this is the y component, so it's away from the angle. That means it will get sine, and here the angle is 70 degrees. Should it be positive or negative? Negative, because the y component is pointing down. Okay, it's pointing down. So that's that. Okay, and how about this one? So we have one more left here. So f x component is cosine theta, and y component is f sine theta. Both are positive because both are pointing along the positive x and positive y. Okay. Now add all the forces in x direction. Okay. F net is all the force TQ sine cosine 10 plus TT cosine 10 or 70 plus f cosine theta. Here f net, I should write here f net in x direction and f net in y direction is TQ sine 10 plus negative T sine 70 plus f sine 10. Okay. And because the system is in equilibrium, the requirement for the equilibrium is there is no acceleration. That means this would be 0. Okay. Or this one also would be 0. So using the condition, this sum would be 0. So negative TQ cosine 10 plus TT cosine 70 plus f cosine theta is 0, and also this sum would be 0. So TQ sine 10 plus negative, I can just write negative, minus TT sine 70 plus f sine 10, not 10, sorry, my mistake, that's theta. Okay, I meant to write theta here. So theta is 0. So we have two equations and two unknowns. So solve those two equations to find the two unknowns. So value of TQ, what's TQ? TQ is 60 newtons, TT is also 60 newtons. So this is negative 60 cosine 10 plus 60 cosine 70 plus f cosine theta is equal to 0, and this one is 60 sine 10 minus 60 sine 70 degrees plus f sine theta is equal to 0. So calculate.
Why is the second one not negative?
Second one, which one? This one?
The 60 cosine 70.
Was it negative? Oh yeah, sorry. Okay. So when I came from this step to that step, I forgot to put minus sign there. Okay. Yeah, you're right. So this one is negative. When you don't write on a board, it's hard to see, so you tend to miss the things. I'm not very used to like writing on the computer, so it's sometimes. So this is negative. Is that right? Okay. So let's do the calculation. So find the value of this and that. So why don't you guys give me a number for this? I don't have calculator, so.
79, negative 79.6.
How about this one?
$46.
46 Newton plus F sine theta. Okay. So we need to solve these two equations. How do we solve? So the way to solve this is take this number on the other side. F cosine theta is equal to 79.6 Newton. Take this number on the other side. F sine theta is equal to negative 46. Okay. And then call this equation 1, call this equation 2. Divide equation 1 by 2 or 2 by 1. Divide 2 by 1. What that means is divide left term by left term and right term by right term. Okay, so F sine theta over F cosine theta. And then on the right side we have negative 46 over 79.6. Okay, can cancel F and F. Sine theta over cosine theta is tan theta. Negative 46 over 79.6. And then theta is tan inverse of that. So let's find that out. Is that negative 30? Okay. So we got the angle. So what is mean by negative 30? First, let's talk about that. So we have this force. Why we have negative here instead of positive? So negative 30 means it's it should be, is that, did you get negative or positive? It should be, seems like it should be positive. because it shouldn't be below x-axis. Negative 30 means it's below x-axis. Okay, if it is negative 30, then this force must be below x-axis. Okay, but why don't you guys double check that? Okay, I'm not sure if this is negative or positive. Oh, okay, f sine theta. So yeah, I think this should be negative. Oops.
I'm still getting -3.
Here, when you do this math, do you get negative or positive here?
I got a negative.
Yeah, so this one should be negative. So this would be negative, so if you do that, this would be positive, okay? And then this would be positive. So you have positive quantity here and positive here, so both are positive. This would also be positive, so that would be positive, so angle would be positive. So it would be not down here, but your force would be up here. So that's 30 degrees. So now let's find the magnitude of the force. Substitute this in one of the equations, either this one or this one. So let's substitute on 1. So put theta is equal to 30 degrees on equation 1. So F cosine 30 degrees is equal to 79.4 Newton. So F is equal to 79.4 Newton over cosine 30 degrees. So that will give you 92 Newton. Okay. If you want to write correct significant figure, it would be 90 Newton. Okay, I think we are out of time, so we will stop at this point. We'll continue this in the next class.
Is there going to be like a study guide?
Yeah, I will post a study guide and a sample exam sometime Wednesday. Yeah,
Thank you.
you're welcome.